In this chapter, chapter 10, we study system of particles. This is the basic concept. In this chapter, we study basic concepts to consider rigid body motion, and from the center of mass, we study center of mass system and the center of momentum frame, and we construct the basic ingredients to attack the problem for collision. So two-body system is mainly considered in this chapter, and considering the central force governed by the inverse square law, we study the conic section, that is the trajectory of the two-body system under the inverse square law. First, let us consider the center of mass of a system of particles. We let xi be the position of a particle, ith particle, whose mass is mi. We treat them, all of them are a massless, the point-like particle. So total mass of the system is a sum of each mass. Right? The center of mass, xcm, of the system of particles is a weighted average of the position with the weight of mass. So product of mass and position summed over all particles and divided by the total mass, capital M, is the center of mass. In the case of continuous mass distribution, we replace this summation with the integral. Right. And the integral, this dm, can be replaced with the density multiplied by the volume element. Right? If we consider collision, the momentum of the system is completely conserved because of the Newton's third law of motion, and it depends that the total kinetic energy sometimes is conserved, sometimes not. And in the case of conservation of total kinetic energy of the system, we say this is elastic collision. In case the energy is not, total kinetic energy is not conserved, then the collision is called an inelastic collision. Let us consider a two-particle collision. First of all, based on the definition of the center of mass, the product of the center of mass and the total mass will be the sum of mass times the position of each particle. The velocity of the center of mass can be computed by taking the time derivative of the position of the center of mass. So if we take the time derivative of both sides, we find the total mass multiplied by the velocity of the center of mass equals sum of the momenta of the two colliding particles. At the CM frame, the center of mass is placed at the origin. So this one is 0. Thus the time derivative of the position is also 0. It is always vanishing. Therefore, the center of mass, the x1 and x2, sum of m1 x1 and m2 x2 vanishes at the center of mass, and sum of the two momenta becomes 0. From this, we notice that the distance from the center of mass to a particle is proportional to the inverse reciprocal of the mass. If we consider a heavy light system is near to the center of mass, and light object is far. All right, the ratio m1 and m2 is the distance inverse of the distance of the two particles from the center of mass. The center of momentum frame is exactly the same as the center of mass frame if we consider the non-relativistic theory. However, if we consider relativistic theory, the two systems are not the same. The more conventional frame of reference in the non-relativistic theory is the center of momentum frame instead of center of mass frame. It is because if we consider relativity, mass is not conserved quantity. Instead of the energy is conserved quantity. Therefore, and the energy is just one component, the time component of the full vector. Because of the full vector conservation for the full momentum requires both energy and momentum are conserved instead of mass is conserved. Therefore, it is good to make use of the center of momentum frame instead of center of mass frame. So center of momentum frame is exactly the same as the center of mass frame in the non-relativistic theory. However, in relativity, we had better to introduce the center of momentum frame to consider the collision problem. While the center of mass is placed at the origin, at the center of mass or center of momentum frame, we are also interested in this simple frame that is called the lap frame. If we consider a target which is at rest initially, and there is an incident particle, and there is a collision, after that they scatter, then the system of reference is called the lap frame. The target is at rest, and incident particle hits the target, and two particles are scattered. Therefore, this is called the lap frame. We introduced a way to compute the velocity of the center of mass measured at the lap frame. This relation is true for in any frame. So the velocity of the CM at lap frame can be computed by dividing the momentum by total linear momentum by the sum of the masses. At the lap frame, this velocity, target's velocity vanishes. Therefore, initial velocity of the incident particle is important. So this is general form. And in the case of lap frame, center of mass velocity will be this one. All right. And at the CM, because it is vanishing, the ratio of the distance from the center of mass to each particle is inverse of the mass ratio. And the same is true for the velocities at the CM frame. We used the following convention for identifying the velocity of an incident particle is initial state. We use u. Initial state u. So particle 1 and 2 identifier will be put as a subscripts. V is the final state velocity. P is the initial state momentum, and Q is the initial state momentum. So this one shows that m1 and m2 collides with the velocities of v1 and v2, and there is a collision, and the initial momentum of the incident particle is p1, initial momentum of the target particle is p2, and the final velocity of the incident particle is v1, and final velocity of the target particle is v2, and q1 and q2 are the final linear momenta of the two particles. And if we do not use the prime, the unprimed variable means the coordinates measured at the left frame, and if we put prime, we indicate that the variable is expressed in the center of momentum frame. As shown in this figure, incident particle m1 hits the target particle m2, which is at rest. At the left frame, m2 target is at rest. The target's momentum is 0. Incident particle of mass m1 has velocity u1. Thus, the linear momentum of the incident particle is p1 equals m1 times u1. The total linear momentum of the system is the p1 plus p2, and because the target is at rest, it is p1 plus p2 equals m1 u1. Okay. Here, capital V is the center of mass velocity, and at the left frame, and in any frame, this is true. But at the left frame, u2 is vanishing because target is at rest at the left frame. Therefore, the total linear momentum of the system is m1 times u1 measured at the left frame. And at the left frame, the center of mass velocity, capital V, is just m1 u1, the total linear momentum of the initial state divided by the total mass. This is the plot. At the left frame, the target was at rest, and initial incident particle is coming in with the u1 vector. And after it hits the target, incident particle moves upward. Sure, it can go downward, but we can always rotate the surface to put the scattered incident particle is moving upward. Okay, the collision of the two particle system is always happening on a single two-dimensional plane. Okay, then the opening angle will be divided into two pieces. We call the angle of the final state in comparison with the initial incident velocity is called the scattering angle. And the scattering angle at the left frame of the incident particle is psi. And the scattering angle of the target particle at the left frame is called zeta. Zeta is similar to xi, but this one is xi and this is zeta. Alright, and then the center of mass moves forwards, and at some point we can connect the two masses after collision. If we connect these two, then it always passes the center of mass. So when M1 and M2 are placed at these two places, at that moment the center of mass is placed in here. And when the collision happens, at that instance the center of mass was placed at that position. Therefore, because the time left from here to there, here to there, here to there are all equal, these three lengths shows the ratio of the three speeds. The center of mass velocity should be along the incident particle because the target was at rest at the left frame. So capital V is this. And the line connecting N1 and M2 at this point, at this instant, is a straight line. Therefore, the scattering angle of the incident particle at the CM frame, theta, and the scattering angle of the target particle at the CM frame, phi. When we sum these two angles, we have pi, 180 degrees, because they are opposite always at the CM frame. Again, at the CM frame, the weighted position, sum multiple mass times position, sum over the two particles must vanish because the center mass is placed at the origin. Because of this, the velocity has the similar relation, and at the CM frame, this x1 dot and x2 dot can be replaced with u1 prime and u2 prime. Recall that we use primed variable for the center of mass, center of momentum frame expression. This is the initial momentum before collision. These are v1 prime, v2 prime. These are the momenta of the two particles after the collision. So there is a straight line made of u1 prime and u2 prime, and another straight line made of v1 prime and v2 prime. Because we have two straight lines, we can always express the collision on a single plane. The interaction of the system can be expressed, described in terms of the force description. The force, net force on a single object in a system of particle, Fi, is a sum of this internal force and external force and internal force. Internal force means all the forces applied to that particle except for that one. For J runs from 1 to n except for I. Okay? So summation of the internal force and external force is the force applied to the system of particles. Center momentum, the total linear momentum is just the total mass times the velocity of the center of mass. And all of the external force can be summed to find the external force. That applies to the acceleration of the center of mass. However, all of the forces in all of the internal forces, they cancel if we sum all over the system. Therefore, the acceleration of the center of mass, the force on the center of mass, is the sum of the net external force, and the internal force sum does not give any change in the total linear momentum. Therefore, if there is a collision of two particles, the two particles gives changes in each to the other particle, but the change of the momentum of each particle are summed to make zero because of the action and reaction. Although each particle momentum changes, the momentum changes of the whole system is 0. Therefore, the total linear momentum is conserved, regardless of the fact whether it is an elastic or inelastic collision. Whether the total mechanical energy, total kinetic energy is conserved or not, the total linear momentum must be conserved. In addition, if the internal force is central, total internal force is central, the torque on the whole system due to the internal torque between any two particles will cancel. Therefore, the net external torque and next external force only changes the total angular momentum of the system. And if there is no external force and the only force applied to a system is the internal force, just like the gravitational interaction between the Earth and Sun, then the total angular momentum is conserved. That means there is a orbital angular momentum conservation for a central force system. In addition, we can consider the kinetic energy of the system, and kinetic energy of the system can be expressed as a sum of this amount. That is just like a point particle of total mass capital M is placed at the center of mass, and it's a translation of kinetic energy of the center of mass as a point particle. And the remaining piece is the kinetic energy due to the relative motion of each particle relative to the center of mass. For a rigid body system, that relative momentum is just a rotational motion. But in the case of celestial body, it may rotate or it may oscillate along the radial direction. So this is a general relative motion with respect to the center of mass. Again, work kinetic energy theorem can be applied to compute the change of kinetic energy of the system. That change of the kinetic energy of the system will be the change of the translational kinetic energy, and for rigid body it is a rotational kinetic energy, but it also has the radial kinetic energy. So relative motion with respect to the center of mass. If we consider a two-body system, the potential energy calculation is simple. However, if we have a system of particles, we must consider that first of all, the potential energy due to the presence of the external force, and potential energy due to the interaction among the particles making the system. Okay, wait a second. Just look at this page. I need some water. Okay, thank you for waiting. And in the remainder of this chapter, we will we will mainly consider the center of momentum frame. So, for example, P prime Cm x prime capital X prime Cm, we just eliminate the subscript to Cm. Consider collision of M1 and M2. This one shows the initial momenta of each particle, of the two particles, and the final momenta. Sure, this momentum conservation states that the sum of these two momenta should be the same in any reference frame. Here, prime variable indicates that we are working on a center of mass frame. All right, let's see. Velocity of the center of mass can be expressed in terms of, at the left frame, the initial incident particle only has the non-vanishing velocity. So initial total linear momentum divided by the total mass will be the center of mass velocity. Alright, so U1 prime, U2 prime can be computed in such a way. U1 subtracted by center of mass will be the U1 prime, because we are making a Galilean transformation by this amount. We subtract U1 by this one. U2 at the left frame is vanishing, therefore U2 prime, that is in the Cm frame, should be 0 minus the center of mass velocity. The result is U1 prime is M2 here. This one is M1. In the denominator, we have M1 plus M2. Therefore, this is M2 U1 over M1 plus M2. And U2 prime is, it is opposite. These two are opposite at the center of mass. We have negative sign, and M1, this M1 U1 over M1 plus M2. Okay. So in general, total linear momentum must be conserved before collision, after collision. At the Cm frame, this capital V vanishes. Right? So in this case, we use the primed variable, and because the sum is 0, U2 and U1 are opposite, and the length is inverse of the mass ratio. V2 prime 2. If the collision is elastic, energy must be conserved. So kinetic energy at the Cm frame will be kinetic energy sum in the final state, kinetic energy sum in the final state, initial state, final state. We know the sum of two momenta in the initial and final must vanish at the Cm frame. Therefore, P1 prime plus P2 prime, the sum is 0. The final momentum sum is also 0. Therefore, if I square these, everything must be the same. P1 prime squared, P2 prime squared, they are the same. This square, they are the same. Substitute this condition in here, we find that same factor multiplied P1 prime and Q1 prime. Thus, all four momenta must have the same magnitude. If the momenta are all equal magnitude, then the velocities are just inversely proportional to its own mass. Therefore, initial velocity, final velocity, they have the same length, same magnitude. Initial velocity, final velocity, they have the same magnitude. Okay? And the ratio of these two is inverse of the mass ratio. Okay, let us introduce a coordinate system. We introduced the coordinate system along z-axis. Z-axis is along the beam direction. Z-axis is along the beam direction, and use the x and y z component. At the left frame, P1 is M1 U1. M1 is along the beam direction. Beam direction. So U1 has the z component only. P2, initial momentum of the target particle. This one must vanish at the left frame. Total linear momentum is just P1 plus P2, and there's M1 U1, and that is total mass multiplied by the center of mass velocity. Because of this, we find the total the velocity of the center of mass should be momentum at the left frame divided by the total mass, that is m1 over m1 plus m2 u1. If we return to the CM frame, this is a repetition, except that we are introducing coordinate system. u1 prime, the CM frame value can be obtained by subtracting the left frame value by the velocity of the center of mass. That is this. And u2 prime, it used to be at rest at the left frame. Thus the CM frame value is a minus v. That is a minus u1 m1 over m1 plus m2. Because if we consider the elastic collision, the magnitude of the velocity, that is the speed, initial speed and final speed of each particle must vanish, must be the same. Therefore, it is good to use the center of mass frame. At the center of mass frame, the final state velocity has the same magnitude as the initial state velocity. Initial state velocity is m2 u1 over m1 plus m2. And we have a freedom to change the angle. Sure, we can make use of the spherical polar coordinate, but we know that the collision surface is only on a single plane. We just consider the y-axis is perpendicular to that plane. Then, introducing angle theta, we are free to make any possible angle of any possible scattering angle. So these all angles are of equal importance. There is no restriction on this angle theta in the center of mass frame, center of momentum frame. Once it is known, because the sum of this final state momentum and sum of the initial state momentum must vanish, the other components are completely determined. They are opposite, and the magnitude is just considered the mass ratio's inverse. Okay. At the left frame, the center of mass frame expression can be used by just taking the Galilean transformation by adding the velocity of the center of mass. If we consider that the result is obtained in this way, okay, just capital V is expressed in here. This one is added to have these components, and all the remaining pieces are just copied from this expression. So V1 prime, center of mass frame's value by adding the center of mass velocity. So we recall that the interaction at the left frame, the initial velocity of the target was at rest, And this is the velocity at the CM frame. The center of mass is flying. Okay, and we recall that this is the angle theta and phi. Sum of these two, the scattering angles at the CM frame, is 180 degrees. However, psi and zeta are rather complicated. Anyway, from this we can write this is the final velocity of the incident particle. This is the final velocity of the target particle. By making use of this scattering angle psi and zeta, this is z direction. Z component is v1 cosine theta, cosine psi, and the x component will be v1 sine psi. And in the case of v2, we have a longitudinal direction. This is the beam direction is called the longitudinal, and this perpendicular to the beam direction is called transverse. So we have a v2 cosine zeta, and this is along the minus x-axis, so v minus v2 sine zeta is there. Right. Then we have V1 expression, V2 expression for psi and zeta can be used to compute the tangent psi and tangent zeta. Tangent cosine, sine over cosine. But we can express this complicated formula in terms of the formula represented in the center mass frame. So this translation by Galilean transformation gives the same value expressed in terms of theta. That theta is the scattering angle at the center mass frame, center momentum frame. Therefore, we have this V1x. This is V1x. V1x over V1z. V1x over V1z. V1x, m2 sine theta, right, over V1z, m1 plus m2 cosine theta. Okay, so we took the ratio, so m2 cancel here, and the m1 over m2 appears here. If you compute the tangent zeta, zeta is this one over this, right? So minus x component divided by z component. Minus x component, there's m1 divided by z component. m1. We have the same mass, so sine 1 minus cosine. And sine 1 minus cosine can be simplified in such a way to have a cotangent to 1/2 theta. So it is as far as psi and zeta is concerned, there are some restrictions. That restriction of angle can be easily analyzed by making use of the variable introduced in the center momentum frame. It is because at the center momentum frame, angle theta is can be freely chosen from 0 to 2 pi, but if we use the polar angle, the polar coordinate system, the three-dimensional polar coordinate system, that is theta is 0 to pi. So in any case, if we choose the velocity v1 is on the first quadrant, then this one is useful. Okay. Next, we consider the initial kinetic energy, scattered particles kinetic energy over initial kinetic energy. So this ratio is so-called particle ones, incident particles recoil energy ratio. Incident particles recoil energy ratio. That is because we are considering the same particle of mass m, just the velocity square will be considered. Velocity of the particle 1 in the final state square divided by the velocity of that particle in the initial state. The answer is already given in here. We have final velocity is expressed in the lab frame in here. So this one is this final state velocity expressed in terms V1 is that this is the final state velocity. This is the final state velocity of the particle 1. This one is to be substituted. So substitution and the straightforward calculation shows this result. And the minimum value, what is the minimum value? When cosine theta becomes, this one is minus 1, so this is 4. That is m1 minus m2 over m1 plus m2 squared, something like that. So back-to-back lesion. That means the greatest momentum transfer appears to the target. Next one, we can compute the kinetic energy of the initial system. Here, at the lab frame, initial momentum is this one, and the target was at rest. And the kinetic energy at the lab frame is given in here. But in the central momentum frame, kinetic energy of the initial system is the sum of the two particles, and we know the magnitude of P1 and P2 prime at the CM frame must be the same. So this one is mu times U1, and mu is the reduced mass. As you know, this is 1 over mu. There's an inverse of a reduced mass. The final result is just like 1/2 mu U1 squared. This is the PR. For the relative coordinate system, PR is mu R dot. And here, this R is x1 and x2 difference. It is not the distance from the center of mass. It is about the distance between the two particles in the two-body system. Therefore, this is actually the relative velocity. These two particles, this is R. So this relative velocity, R dot, is just U1 of this initial case. There's a lab frame case. At the CM frame, this U1 and U2 equals 0. U1 and U2 in the lab frame. The CM frame, they are just U1 prime minus U2 prime. Because the Galilean transformation gives the change by the same magnitude, they cancel. So U1 minus U2, that is U1 and the lab frame. So relative velocity is relative velocity at the lab frame, is the relative velocity at the CM frame, and that is the time derivative of a relative coordinate, right? Relative coordinate. That is the magnitude of the x1 minus x2. That is very, very important. So CM frame total kinetic energy is just, if we substitute the reduced mass, it can be converted to the initial kinetic energy of the left frame, and that is smaller than the value measured at the left frame. In this case, we can compute the fraction, recoil energy fraction, and it's straightforward to compute. So let me leave it to you, just follow these calculations. The recoil energy fraction can be computed by finding the ratio of the momentum, initial momentum, final momentum to initial momentum of a particle 1. And that is coming from the conservation of mechanical energy. And here momentum conservation can be applied. Momentum conservation can be applied to replace this one. This one is the left frame. Q2 is replaced to P1 minus Q1. And if we expand all this, we can find the quadratic equation for rho. Rho is the ratio of magnitude of Q1, magnitude of P1. The final momentum to initial momentum magnitude ratio for the particle 1. That's incident particles. So, solving the quadratic equation, you find the answer. Okay. The corresponding ratio for this is the momentum ratio. The energy ratio can be computed in this way by squaring this answer. Now we can also compute the recoil energy of the scattered particle, target particle. So target particle's energy divided by the incident particle's kinetic energy at the left frame can be computed in a similar manner. Kinetic energy conservation is applied. Now we are interested in the Q2. Therefore, we can make use of the conservation of momentum and replace the Q1 with the P1 minus Q2. Now, expression becomes greatly simplified to find the answer for the Q2 over P1. So that result is this one, and substituted to find the recoil energy fraction for the target particle. Okay. Now let us consider some collision of relativistic particles. In this case, we simply consider the two-body collision to make a particle at rest. If we consider the relativity, energy of a particle is expressed in this way. There is an unsure condition for a particle is energy squared subtracted by the momentum times the speed of light squared is the rest mass squared multiplied by c to the fourth power. Therefore, the rest mass of the particle can be computed by taking the square root of energy squared minus pc squared divided by c squared. Okay. We know the p mu is the full displacement. That is the simplest four vector that represent the time and space. This four vector the four vectors transformation is governed by the Lorentz transformation And under the Lagrangian transformation, the square of a full vector is invariant. Square of a full vector is expressed as the time component square subtracted by spatial component squared. And as far as this full displacement is concerned, that value is just c times speed of light times proper time squared. This one can be extended to find that the full momentum is also a full vector. If it is a full vector, the square of the full vector must be conserved. At rest frame, this momentum becomes 0, and this square, time component square, subtracted by spatial component square, satisfy the unsure condition for massive particle. Alright, by making use of this relativistic background, we can compute the magnitude of momentum of each colliding particle to make a particle at rest. As we know, the sum of the two masses are not the same as the capital M. Instead, the capital M times the c squared, that is the energy, rest energy, of this particle at rest at the center of momentum frame is the sum of the two energies of the two particles. And energies of the two particles can be computed in this way. The two particles collide at the center of momentum frame. Do momenta cancel exactly? And a heavy particle is produced, and it will be at rest at that position. Therefore, four vector conservation states that the total linear momentum, total full momentum of the final state, the full momentum of the final state should be the same as the sum of the two full momenta. That is, this is the first full momenta, this is the second full momenta, and this is the final state full momenta. If we copy these first elements, and we have the energy conservation, E1 plus E2 equals E over C. But when momentum becomes 0, E over C should be M0C. This is M0 is a capital M. Therefore, we have E1 plus E2 equals MC squared. This one. E equals this one, but we have momentum P equals to 0 vector to have MC squared. Alright, the energy sum of the two vectors will be expressed in this way. However, we used P1 squared here, P1 squared here too. The reason is that we are working at the center of momentum frame. At the center of momentum frame, the sum of two momenta is vanishing, so P2 can be replaced with minus P1 after square, they are equal. To solve this equation to find out the magnitude of P1, we just make a following substitution. First, divide these equation by c, speed of light. And mc is replaced with x, m1c is y, m2c is replaced with z. And absolute value of momentum P1 is replaced with alpha. Thus we have x equals square root of y squared alpha squared plus square root of z squared alpha squared. Now, the equation can be solved by moving this square to the left and take the square. If you take the square, x squared minus 2x square root and square of this is y squared plus alpha squared. This side is z squared alpha squared cancel. Now we still have a square root. Move this one to the right and flip the left and right, and move this z squared to the left. That is this. Now we take another square. This 4x squared y squared alpha squared equals squared. We can move this 4x squared alpha squared to the right side. 4x squared y squared. That is a square of 2xy. Now we find that this is factorizable. If we factorize 2xy plus 2xy minus. Now the left hand side 4x squared alpha squared, and right hand side is just factorized in this form. We find that sum of 3 and sum of 2 and minus something. Sum of 2 and minus something. So if we pull out negative sign from it, we have over negative sign and sum of xy minus c, sum of yz minus x, zx minus y. This is a triangle function. This factor appears in the Heron's formula for the area of a triangle. You know, sum of the two sides of a triangle is always greater than the other one. So if this one is a positive, x, y, z make a triangle, right? So this formula is called the triangle function or Kellen function. By making use of the Kellen function, the magnitude of P1 and P2 at the CM frame are expressed in terms of alpha, and that is c. This is speed of light, c over 2m, square root, Kellen function, m squared, m1 squared, m2 squared. Energy of each particle can be straightforwardly computed, and the result for E1 energy of the first particle 1 is 1 over 2m, this guy divided by multiplied by c squared. Notice that E1 we have positive sign in front of m1 squared. E2 positive sign in front of m2 squared, and subtraction is made for the other particle. That's very, very important for particle experiment and the high energy theory or experiment students involved in the high energy physics. Now, let us consider our final step in this chapter is to consider the central force motion governed by the inverse square law. You may have expected that we are considering the conic section, that is the trajectory of the central force governed by the inverse square law. First, we recall that the central force motion involves the conservation of orbital angular momentum. Conservation of orbital angular momentum states that the orbital motion is placed on a single plane because the direction of angular momentum doesn't change the direction, and the rate of rotation for mr squared theta dot is fixed. That means the orbital motion is always isolated on a single plane. Therefore, that kind of problem can be fully described by making use of two-dimensional polar coordinate system. The Lagrangian of that central force motion of the two-body system is completely expressed in this way. We have already studied that. This one must be mu. We call that mu is the reduced mass, and r is the relative coordinate. This is not the distance from a particle from the central mass, but the relative distance of the two particles making interaction. because the potential energy does not have any theta dependence, we have theta to be the cyclic coordinate. Theta is the cyclic coordinate, therefore the angular momentum, conjugate momentum for the generalized coordinate theta must be what? Conserved. Therefore, orbital angular momentum is conserved. Kinetic energy of the system is written in here, but because this orbital angular momentum is conserved, L is constant. So we can substitute theta dot with this to find that kinetic energy has the radial kinetic energy and rotational kinetic energy. This rotational kinetic energy can always be expressed in terms of angular momentum square over r squared. That's quite important. Now, because the Lagrangian does not have an explicit time dependence, round L over round T equals 0. We recall that the second form of Euler-Lagrange equation and Hamilton's equation states that the total time derivative of Hamiltonian is the same as the partial time derivative of the Hamiltonian and is equal to minus a partial time derivative of Lagrangian. If we apply this, the Hamiltonian must be conserved. We have two components. Hamiltonian is conserved and p theta is conserved. By making use of these two conserved quantities, we can simplify the expression for describing the system governed by a central force following the the inverse square law. All right. Orbital angular momentum conservation states that theta dot equals L orbital angular momentum divided by mu r squared. Because of this, angle change is proportional to the angle at time change. So angle can be related to time, 1-to-1 correspondence, up to over factor that is 1 over r squared. Conservation of Hamiltonian can be applied to replace the Hamiltonian with the constant value that is the total mechanical energy of the system. Now we applied inverse scale law. Inverse scale law states that U equals minus K over R. For attractive force, K is positive attractive, K is negative repulsive. Okay. Substitute U here. Now, R dot squared can be expressed in terms of this. If I take the square root, we have positive or negative sign on it. Positive means R increases as time goes on. Negative means R decreases as time goes on. For example, two particles collide with a repulsive force until they reach R minimum. This is R minimum. When they are closest, this R is decreasing, so R dot is negative. And then when they, after the collision, they are going far and far away. So decrease, increase. Okay? Distance, decrease, increase. This kind of way. Now, because dr is related to dt, dt is related to dr. In such a way, we divide this square root both sides. Now, theta dot is L over mu r squared, the angular momentum conservation. So I can replace this d theta with the dt, and eventually dt is replaced with the dr, because we know this r dot is dr over dt. Thus d theta, that is orbital angle change of the orbit, this is the theta dot dt, theta dot here, theta dot here, theta dot, and dt. And dt equals dr over square root plus minus. As I already told you, positive sign is going far away, negative sign coming, they are approaching. Now, let us consider Kepler's first law before the end of this class. Kepler's first law is conic section, and usually people understand it is a theory of ellipse, but it is in general ellipse, parabola, and hyperbola. So all three kinds of the geometric object is a conic section, cross-sectional area, cross-section of a cone. So Kepler's first law, the angular momentum conservation is to be used. This angular momentum conservation states that the dt is related to d theta. From this, we can replace the derivative with respect to time with derivative with respect to angle theta. If I repeat this one twice, then I have L over mu r squared angle derivative, L over mu r squared angle derivative twice. The Euler-Lagrangian equation states that we have radial equation is like that. Radial equation, R derivative, this one, centrifugal force, mu r theta dot squared. This is a real radial force, and radial conjugate momentum's time derivative, right? Now, this one is moved to the right and flip the direction, flip the two sides, reduce mass times double time derivative of r, and centrifugal force and radial force. Now, this if I substitute the theta dot equals L over mu r squared, then I have this contribution and force. What we have found is that double time derivative, it can be expressed in terms of the angle derivative. Double time derivative here, so put mu here, and the double time derivative is written in here. Now we find that 1 over r is a good variable for treating this problem. 1 over r, we replace the 1 over r by a variable u. Then derivative of u, differential of u is minus 1 over r squared dr. That means derivative of r means a minus u squared du. Substituting these results in here, we have a mu L over mu r squared. R squared disappears. This negative, the r squared is replaced with u squared. Okay, and d theta L squared over r squared. We replace this one dr over r squared. dr over r squared is replaced with minus du. So replace this one, r squared is replaced with minus du. Right, and right side it is a u cube, and this r derivative. R derivative is a minus u squared, so plus u squared potential energy derivative with respect to u. Now I have negative sign And we multiply both sides with the mu L squared over mu squared, U squared. We end up with this expression and migrate this one to the right and move this one to the left. Then this guy becomes double angle derivative, and u is this, right? And this one is migrated to the left. We have this one. We consider the potential energy. UR is a minus K over R, right? If we substitute U is 1 over R, take the U derivative, you find this is just a minus K, simple one. Therefore, this one multiplied by minus K is a mu K over L squared. We end up with the second order differential equation. Then the equation of motion reduces to harmonic oscillator form if it were zero. This is a harmonic oscillator with the constant force. Okay, so particular solution can simply apply. This one is particular solution. This one is constant, if I take the theta derivative, it vanishes. So this one is the simple particular solution. We introduce, this is semi-lattice rectum alpha, L squared over mk. So this is particular solution is 1 over alpha. The general solution for the homogeneous equation, this equals 0, is just the cosine, amplitude, and phase, right? Therefore, the general solution of this system is particular solution and general solution for the homogeneous equation. If I pull out 1 over alpha out, then we have 1 over alpha, 1 plus epsilon cosine something. This theta 0 can be chosen by changing the axis of symmetry. So eventually it will be expressed this is 1 over alpha. So alpha over r equals 1 plus epsilon cosine theta. If we set theta 0 equals 0. Or r equals alpha over 1 plus epsilon cosine theta. It is interesting to find that this is a conic section. This is conic section. Conic section, we have list of variables. Alpha is a semi-lattice rectum of each conic section. Epsilon equals 0 circle. Epsilon 0 between 1, this ellipse. Epsilon equals 1 parabola. Epsilon greater than 1 hyperbola. And all these conic sections are completely determined by this simple polar equation. All right. So in the next class, we study all of these examples, how the geometric structures of the orbit are related to the physical variable. For example, this epsilon is the eccentricity, alpha is a semi-lattice rectum. They are completely determined by the mass, strength of the force, orbital angular momentum, and total mechanical energy of the system. Okay, we expect that we have complete view on the Kepler's law, and this approach is very useful for studying the hydrogen atom system in the even quantum mechanics. Thanks.